All right. So welcome everybody to CIRCUS, Harvard Center for Research on Computation and Society. It's really exciting to kick off this Rising Stars in AI series, focusing first on health. My name is Milind Tambe. I'm director of CIRCUS. CIRCUS as a center focuses on use of computation in public health, conservation, equity, and fairness. In addition to projects that we run, we have a set of events. In fact, this whole month, we have a lot of events focusing on definitely our seminar series in AI for social impact, as well as these Rising Star events throughout this month, AI in Health Equity panel, and others. Please look out for our website, our announcements on social media. I hope you will be able to join many of these events. I wanted to thank the organizers of this Rising Stars in AI event, Jackson Killian, Lily Shu, and Aditya Mate, for doing a tremendous job putting this event together. So with this, I'm going to hand this over to Jackson and Aditya to moderate the panel for today. Thank you.
Great. Thank you so much, Milind. So yeah, I'd like to, again, thank all the organizers, but then especially thank our four wonderful speakers that we have today. So really excited to hear from each of you. All of the speakers here today were nominated by experts in AI for social good, including faculty members and some postdocs across the field. And this is, an awesome recognition of your achievements here. These folks were really impressed by your exemplary research in the field. And so without further ado, let's get started with the talks. Today, we will start with Charles, actually, let Aditya and I'm Jackson Killian. I'm a PhD student at Harvard in computer science and a third year also doing work in AI for public health. So very interested, especially in this panel. And let me let Aditya introduce himself too, who'll be my co-host today.
Thank you so much, Jackson. So I'm also equally delighted to be participating in this and organizing this series, and very excited to hear from all four of you. Congratulations and thanks again for joining us, and looking forward to hearing. Thank you.
Excellent. So with this, I will stop my share. We're going to start with Charles. Charles, are you ready? I'll give you a brief introduction. Just want to make sure you're here and ready.
Yes, I'm here and ready.
Excellent. Okay. So our first speaker here is Charles C. Onu. He will be presenting his work on robust algorithms for the analysis of infant cry sounds to detect pathologies. Charles conducts his research at the intersection of artificial intelligence and healthcare at Mila and the Reasoning and Learning Lab at McGill University. His supervisor is Professor Doina Prekup, co-director of the RL Lab and director of the DeepMind Lab in Montreal. The overarching theme guiding his work is advancing machine learning to positively impact healthcare. Specific areas he works on include classical ML, deep learning, speech, physiological signal processing, and tensor decomposition techniques. He holds a Vanier Canada Graduate Scholarship. He also founded and led AI research at Ubenwa. The Ubenwa project is aimed at developing cry-based, low-cost tools for the early diagnosis of conditions that affect the central and autonomic nervous systems in newborns. The work is funded by generous grants from MILA, Ministère de l'Économie de l'Innovation, MEI de Quebec. I apologize if I mispronounced any of that. District 3 Innovation Center and MIT Solve. So Charles, please take it away.
Okay, thank you, Jackson, for the introduction. Just to check, you can see my slide and you can hear me well. Okay, I see the
Yes, perfect. Yeah.
Okay, thanks. So I'll dive right into it. I'm going to start by playing two nice, calm, relaxing audio samples for you. So first, and this second one. Okay, so if you heard that, you were probably thinking that was not so relaxing. But I'm sure you also recognize that those are sounds of babies crying. And I hope they got your attention, because the crying of babies is basically how they communicate their needs to the outside world. But what is not well known is that the baby's cry can also tell us about its health and how it's doing physiologically. So sample 1 was from a normal, healthy newborn, while sample 2, on the other hand, is from a newborn that's suffering from birth asphyxia. A newborn's cry is an involuntary action that is directly coordinated by the central nervous system. And so when there's an injury, when there's a condition that causes an injury to the brain, this is reflected as changes in the cry patterns. And so while you may not have been able to tell the differences between the two samples I played, upon analysis of the spectrograms and the waveforms of these samples, there are actually significant differences between them. For example, asphyxiated babies have higher fundamental frequencies, dysphonation, and more instability in their pitch sounds. So why do we care about asphyxia? Well, asphyxia happens when the newborn is unable to sustain some spontaneous breathing in the period after birth. And what happens is this results to a shortage of oxygen supply to the brain, which in turn, as you can imagine, will result to the brain cells dying, injury, potential disability, or even death. Every year, there are about 140 million babies born, and asphyxia alone is responsible for over 2 million casualties, making it one of the top 3 causes of infant mortality today. So clinical diagnosis of asphyxia requires the combination of blood, neurological, and physical exam, which together constitute a costly procedure that requires specialized equipment and trained personnel. What happens is that in many developing countries, in low-resource settings, only the physical exam is available, and this drives higher newborn mortality rates. So a couple of years ago, I started working on the problem of detecting asphyxia from cry sounds. I obtained cry data from a Mexican hospital containing cries of normal and asphyxiated babies. And what I did was develop machine learning models using support vector machines to show that using only the cry as an input, we could detect asphyxia with up to 86% sensitivity and 89% specificity. So what this meant was that in settings that could not afford blood tests and neurological exams, we could potentially improve the screening accuracy by up to 40%. And so this was great news on one hand, but I quickly realized that it was just the beginning of this work, because to deploy a medical screening tool that is reliable enough to function, we need to develop it and test it on more than just 70 patients that we had in this database. And in addition, there were also several research problems that emerged that needed to be tackled along the way. And so because I was looking for innovative ways to complicate my life, I went on to subsequently start a PhD, as well as launch a startup. The PhD was an opportunity to work with some of the best minds in machine learning and neonatal research, such as my advisor, Doina Pickup, while the startup was an important vehicle for bringing this work to reality. So for the rest of the talk, I will briefly highlight 3 of the projects that I'm working on during my PhD, and also use the rest of the time to highlight what we're doing at Paidmoyo. So first, one of the things we quickly found in the SVM-based model was that for asphyxia detection was that it had many failure scenarios, many simple failure scenarios even. Small perturbations in the test data led to wild and different results at times. And part of the problem was that we did not have enough data to learn robust decision rules. And so in this work, what we did was we explored the idea of transfer learning from adult speech to infant cry sounds. Since there are countless openly available data sets of adult speech, the question was, could we leverage this somehow to improve performance in our models? And the intuition here was that even though adult speech is different from cry sounds, they do have some similarities. Both are harmonic sounds that have a pitch and generated formants, and they're essentially generated or driven by the same physioacoustic mechanism. Vibrations of the vocal cords, and then the modulation of these through the laryngeal tracts. And so in this work, we learned discriminative feature extractors based on CNNs, convolutional neural nets, using the adult speech data. And then we fine-tuned them on infant cry data. And what we found was that, on one hand, these models were slightly more accurate than the ones that didn't use this transfer learning approach. but they were significantly more robust to distortions in both the time and frequency domain. And I invite you to check out our paper for more details on the methods and experiments and the results in archive. In another project, I tackled the problem of model compression in neural networks. It's probably common knowledge today to everyone, both within and outside the field, that neural nets tend to require millions of parameters to get high-performing models. But what this also means is that it results to large memory requirements and potentially slower models on mobile devices, slower than the instantaneous responses we've come to expect from smart devices. And so the topic of model compression has actually been well studied in machine learning. And you find that if you're familiar with the area, you find that there's basically one paradigm in which you, first of all, train a large model, and then secondly, you apply some technique to trim this model. And one challenge with this approach is that it's time and resource consuming. And the second stage could lead to the model diverging from its goal, such that in many cases, you actually would have to do a third stage of fine-tuning the model again on the training data to get your final compressed model. And my main contribution here was developing an approach for end-to-end training of the compressed models. Essentially is, could we have a single step in which we directly train the model that is already a compact architecture? And so how did we go about this? The core idea we used was that of tensor factorization. So basically, instead of using the standard tabular format for representing these large weight matrices that we have in neural nets, we use the factorized format. This is similar to matrix factorization, except that we employ tensor decomposition methods, where we first reshape the matrix into a tensor, and then apply this decomposition in the tensor space. And we do this for all the weights in the network. And there's more detail to the method. I simplify it here. So you can also look at the paper. But to summarize the results of this, what we found was that this resulted in impressive compression rates, going from millions of parameters. For instance, the LSTM we have here has over 3 million parameters, and reducing that to about 13K parameters in the tensor train LSTM that we developed, and having minimum impact on the performance. But you find that it also has better properties in terms of regularization and also gradient stability, which are some of the experiments you find in the paper. The third project I'll talk on, which is more of an ongoing one presently, is in my PhD, is one of learning task invariant representations that can be reused for multiple tasks. So a typical CRI analysis system in production would involve several models, each extracting different pieces of information from the data. One doing CRI detection, one identifying the speaker to make sure that the right results have been assigned to the right patient, and another doing the actual pathology detection, for instance. And the question here is that, is it possible to develop a single feature extractor that is useful for several tasks, such that only a simple classifier is required afterwards to make the prediction? This means that computation can be shared across the task, leading to faster real-time processing and effectively smaller size models. And here we are looking at the rich literature in multitask learning, in machine learning, but also potentially more generalizable approaches like self-supervised learning for this. So where is this all going? As I mentioned earlier, it's critical that we translate this work to reality. The problem of asphyxia and in general access to rapid diagnostics is one that still affects millions every year. And this is where my team at Paidmoyo and our clinical collaborations, collaborators come in. So with collaborators in Brazil, Canada, and Nigeria, we are conducting large clinical studies to acquire more data and to validate our algorithms. The goal is to collect about 2,500, recruit 2,500 patients and collect fully annotated CRI samples with clinical indications. This work is ongoing. I think we're at about 300 patients right now. And we are incorporating our models into the Paidmoyo mobile app. The app is a simple tool that would allow health workers in 3 simple steps to analyze the infant's cry and to determine if the baby is at risk of asphyxia. As you might imagine, compared to the current standards for diagnosis, it's faster, it's cost-effective, it's non-invasive, and requires little or no expertise to operate. To finalize, Ubenwa means the cry of a baby in my language, Igbo, from Nigeria. And our vision is to harness AI to empower health workers with accessible cry diagnostic tools that could save millions of babies that are affected by different conditions that could really benefit from early detection. I'll be remiss to not acknowledge the tens of people who have been a part of this work over the last few years, starting with my advisor, Donna Frickoff. I would not be able to embark on the adventure I've been on without her support and guidance. And my unofficial advisors, Professor Kearney and Guilherme Santana, the Ubenwa team as a whole, our clinical collaborations. And my PhD has also been funded by the Canada Graduate Scholarship. And I also thank all the sponsors who have been helping us at Ubenwa make this happen. And thank you for listening.
Thank you so much, Charles, for the really interesting talk. So I'm sure many people have many questions, but so what we are going to do is we are going to let all the 4 speakers speak first, and we'll take all the questions at the end. With that, let me quickly introduce the second speaker. So I think the second talk is going to be by Irene Chen, and she's going to be talking about her work on beyond bias audits, building ethical machine learning for health pipeline. Sorry. So let me also quickly introduce Irene. So Irene is a PhD student in the computer science department at MIT, advised by David Sontag in the clinical machine learning group. She works on machine learning methods to advance understanding of health and reduce inequality. And prior to MIT, she completed a joint AB-SM degree at Harvard. She has also worked at Dropbox as a data scientist and machine learning engineer and chief of staff. So over to you, Irene.
Thank you so much for that introduction, Aditya. I just wanted to say I'm super grateful to be presenting today. As Aditya mentioned, I did my undergrad at Harvard, but we didn't have Circus at that point. So I'm very excited to see great work continue to come from Harvard and seeing what this institution can continue to do. And many thanks to my collaborators, without whom this research would not be possible. All right, let's go. Today I'll be talking about thinking beyond bias audits, so building an ethical machine learning for healthcare pipeline. As many of you in this talk probably know, machine learning has tremendous promise for healthcare. So right now, sort of powered by large observational clinical data sets, machine learning models have been shown that they can actually beat human experts, or at least match human performance, particularly in well-scoped tasks, for example, medical imaging tasks. The regulation for these algorithms continues to evolve in America, that's the FDA, to figure out what do these algorithms need before they're approved, before they can be used widely in a real-world high-stakes setting, for example, a clinical hospital. Practically what this means is that you might enter the hospital, your doctor may use a machine learning algorithm that has been trained on past patients and been treating with existing protocols. And using all that data, the doctor takes into account the machine learning risk score and uses that to determine patient care. The problem, as we've started to roll this out, is that we've discovered that we want to make sure that our algorithms are not perpetuating existing inequities. And what I mean by that is that although algorithms are often inscrutable, we're starting to get insight into ways that bias may manifest. So for example, dermatology data sets that are used to train deep learning algorithms, these medical tasks that can compete with humans, these data sets actually primarily come from fair-skinned patients. And we can imagine this percolates down and contributes to errors, for example, on specific types of different types of skin tones. And another example, researchers have shown that care management algorithms, so these are programs that insurance companies use to proactively reach out to patients who need extra support because they'll have extra health need in the next year. These algorithms were trained on future health cost as opposed to health need, and therefore demonstrate racial bias. So often these bias results are found by looking at certain subpopulations and identifying, there's actually bias going on for different groups. It's important, though, that we want to keep the entire model development pipeline in mind. So bias audits, as you can see from this diagram, are only one piece, really the end of a very long model development pipeline. Then the question becomes, and what I want to talk about today, is how can we start thinking about incorporating an ethical lens? What can we do so that we're not relying on one piece at the very end of a pipeline to catch everything, to fix everything? And rather, what do we do once now that we've started to uncover different amounts of bias from these audits in machine learning algorithms for health? Today, I'm going to talk about two case studies. I know it's tight to fit into a 12-minute talk, but I'm going to try. One, we'll be looking at how, once we've audited a score, how can we fix what's going on? How can we figure out where to address resources to fix existing risk scores? And then the second, we'll look at how we can use algorithms to directly model health inequities in the first place. So in this case, we want to use domain knowledge to improve our model itself. We want to infer a latent variable. For here, we'll be referring to access to care, when patients receive care in the first place. All right. So first example, diagnosing sources of unfairness in supervised learning. One of the first algorithms I ran in my PhD was looking at predicting patient mortality in the intensive care unit. We took the clinical notes from the first 48 hours and we used it to predict whether or not a patient will die in the hospital. We found that there are actually differences in accuracy based on the patient's self-reported race. The natural next question becomes, well, what do we do now? At the time, there was a large branch of fairness literature going on that looked at how we can balance, say, accuracy and fairness. So here we see that group A has less error than group B. And if we wanted to improve the fairness or the disparate impact of the algorithm, one example could be that we could increase the error for group A. Now, the difference between them is smaller. This is a trivial example, but methodologically, often we use regularization parameters or fairness constraints in order to do effectively this. In medical settings, this is not palatable and is probably unethical in the first place. Instead, if we look at a wider range of actions, for example, instead of only looking at the model, we can look at the training data that's incorporated into the process. We start to develop a few more tools so that we can leverage. One way is to decompose the amount of unfairness that we detect into statistical components. So here we look at statistical bias, variance, and noise. Most people, when they think of sort of bias audits, they probably think of the sample size as contributing to a model performing poorly, meaning maybe one group is much smaller than another, and therefore that's why it has much worse error. This is deemed variance, so the sample size is contributing to the unfairness. Additionally, however, bias and noise can also contribute. Bias here, statistical bias, refers to the model class fit. For example, linear or nonlinear models, you're using a linear model when you really need a nonlinear model. And then noise refers to the irreducible error. For example, if the measurements are faulty. So even if we had infinite data and the best possible model class, you still can't get that perfect error that little error that you're looking for. We were able to show that you can actually decompose cost-based fairness metrics into a difference in bias, a difference in variance, and a difference in noise. And we were able to show different ways you could detect which component is contributing to the unfairness and therefore address it accordingly. Put another way, if you had $1 million, you want to figure out which one you can put it into and not, for example, spend all $1 million trying to solve the unfairness problem, but put it into the wrong statistical component. Each component has an actionable step and that can guide model practitioners for a practical way to do what to do after a bias audit. Switching gears a little bit, we can also think about ways to build these considerations of inequity directly into the model. I kind of glossed over this amount of noise, but it turns out systemic health inequities can contribute to noise in the measurement. So when we see patients, the data itself is already starting to be not quite as descriptive for some patients as others. Today, we'll focus on access to care, meaning that not everyone can see the doctor as often as they might need. As a motivating case study, something that we were interested in, we were looking at disease phenotyping. So Scientists and clinicians are interested in how chronic conditions develop over time, and it turns out some diseases may develop completely differently, and the study of this is disease phenotyping. If we put our machine learning hats on, we could actually use observational data and learn these phenotypes using machine learning. Problem is that data can be hidden from observation. For example, before a patient is diagnosed, we don't get any data from that patient. So we call that left censorship because it happens on the left side because time moves left to right. In fact, a lot of factors can impact left censorship. For example, access to healthcare. So the question then becomes, how can we learn disease phenotyping while accounting for left censorship, which is essentially access to care? We developed a deep generative model, specifically a VAE, that learns both the alignment of the patient, so essentially estimating how much left censorship, how much access to care allowed them to come in earlier in the progression, as well as the subtype of the disease, so which phenotype did we learn. Both the alignment term and the subtype term are latent variables in our graphical model, and we were able to show sufficient conditions for identifiability. We were able to derive a variational inference approximation to the data likelihood to learn for our VAE. And we have experimental results that recover known clinical findings, specifically on Parkinson's disease and heart failure patients. Going into our results a little bit more, we were able to outperform baselines on synthetic data. We were able to recover Parkinson's control and Parkinson's disease patients. We were able to identify them pretty clearly. And our results are robust even to misspecification. But I want to sort of take a caution ahead approach. So where do we go from here? What can you, an audience member, remember from this presentation and think about and bring it to your own work? The truth is, after I made a big stink about the pipeline and how we want to cover all of it, we only covered a little bit more of the pipeline today. We extended into the algorithmic development and also what to do after your bias audit for post-deployment considerations. But there are many other steps we didn't even touch on today. As one last highlighting example, I want to talk a little bit about my newer work looking at intimate partner violence, or IPV, which is defined as physical, sexual, psychological, or economic violence that occurs between former or current intimate partners. So how can we think about intimate partner violence in the context of this model development pipeline? So the first step is actually, what are we studying in the first place? This is something we should really scrutinize. What are we funding? What are we deciding to focus on? The CDC reports that 1 in 3 women and 1 in 10 men will experience IPV in their lifetime, which is a pretty staggering statistic. So how do we identify what are the important problems to solve? Once we've gotten there, what data should we collect? IPV is prevalent but underdetected, so focusing only on clinical data might be limiting. We want to gather as much data as possible, as many modalities, so we can build the most representative models. And then once we have this data set, even the problem of defining what we're predicting can be tricky. So prior work has often used clinical diagnoses, which can rely on a clinician's judgment, or patient self-reporting, but that can ignore sources of stigma that makes people reluctant to come forward when they're victims of IPV. So we need to really start thinking about the entire pipeline, not just the last 2 steps, but all the steps. So in conclusion, bias audit, just the beginning. I'm really excited that we're getting this attention. People are publishing papers and illustrating that there's bias going on, but we need to think about what happens after that. We need to learn how to address once the bias is found and build those considerations earlier into the pipeline. And in fact, thinking about the entire pipeline in the first place will propel machine learning forward, specifically machine learning in healthcare. Thank you.
Excellent. Thank you so much, Irene. And again, we will hold questions until the panel session at the end. If you have questions, please feel free to post them in the Zoom chat here. Okay, so next we will have, switch over the spotlights. So Paidmoyo, if you are here, would you let me know?
Oh, morning, Jackson. I'm here. Thank you.
Hi, good morning. Great. Okay, so I will quickly give you the introduction here. Great. So Paidmoyo Chapfuwa received BSc with distinction, MS, and PhD degrees in electrical and computer engineering from Duke University, Durham, North Carolina in 2013, 2018, and 2021. expected, respectively. Paidmoyo has been advised throughout her PhD by Drs. Lawrence Karen and Ricardo Heno. Her research focuses on developing modern machine learning approaches, i.e. representation and deep learning, to characterize individualized survival event times from clinical data, such as electronic health records, and more recently, immunomics. Her work incorporates statistical techniques from causal inference, generative modeling, and Bayesian nonparametrics. Her work is culminated in publications in prestigious venues such as IEEE, ACM, ACL, and ICML. So, Paidmoyo, please take it away.
Thank you for the introduction, and I am happy to be here. So today I'll be talking about my recent work in counterfactual survival analysis with balanced representations. And so in this work, we're mostly interested in estimating the causal effects of a given intervention or treatment on survival time. And so what that means is that when we have a new patient coming into the system, we need to decide what treatment to assign the patient. And so we can look at the survival curves of the two treatment groups, which is treatment A or treatment B, and then we can decide whether to assign treatment A or treatment B to the new patient. And so the gold standard of doing causal inference in survival analysis is to use randomized controlled trials. However, these are usually long-term engagements and they're expensive and limited in sample size. And so in my work, we focus on augmenting these RCTs with observational data, and so that we can either verify or And so the main challenge with using observational data is that we have selection bias. And so in this work, we focus on selection bias, which is due to confounding. And so, for example, we can have confounders that affect both the treatment and survival time. And for example, in certain situations, age usually affects both the treatment assignment and the survival time. Another challenge that we have is that we observe factual outcomes while the counterfactuals are typically unobserved. And so this second challenge with observational data is that we have censoring bias. In this work, we mostly focus on right censoring problem, which could be informative or non-informative. However, other censoring mechanisms can be considered as well, such as left censoring or interval censoring. And so here I actually illustrate an example of a typical data set that we can have in a clinical setting. So we have, for example, the first two sets of patients who have received treatment A, and we have another set of two patients who have not received treatment A. And so you can see that in both these scenarios, we have censoring. And when the censoring is right censored, so it means that the actual event time happens to the right of the observation window. So when we build models, we need to account for this censoring mechanism and also confounding. And so first, I just want to give you a brief introduction of how we can typically characterize time to event. And so in practice, we are mostly interested in the risk function or what is commonly known as the hazard rate function. And this is a ratio between the event density function and the survival function. And here I actually show some examples. For example, if we assume an exponential event density function, what that means is that we're assuming that the risk is constant over time. However, this is usually violated in practice because the risk can actually increase or decrease over time. For example, if you have had surgery, your risk of infection can increase and then it can decrease over time. And so in those scenarios, we may want to use flexible distributions like the Y-bar or the log normal. And so typically these data sets are used in healthcare to estimate risk or treatment planning or drug development. However, the methods that I talk about here general, and they can be applied to other domains like in manufacturing for equipment manufacturing. And so to be able to use observational data, we have to make some causal assumptions for identifiability to hold. And so the first assumption is that we have consistency, meaning the treatment assignments between the units are IAD. We also have the ignorability assumption, meaning all confounders can be measured. We have the overlap, meaning we have a shared covariance support between the treatment groups. And then we have to make some assumptions on censoring. And so since we actually don't know what the censoring mechanism is in practice, we have to model for both censoring mechanism, which could be informative censoring or random censoring. And so typically we wish to estimate the individualized treatment effects using the characterization of time to event, which I talked about, which could be either the survival or the hazard function. And this is based on the potential outcomes. And so I actually show here, we have the two survival curves. We may be interested in the difference in this, in the expected life, which is the area under the curve between the survival functions, or we may be interested in just the difference in those functions, or we may be interested in the hazard ratio, which is actually what is used in practice because it is considered more informative. For example, a hazard ratio, which is less than 1, indicates that the treatment assignment is positive. And so we actually propose a model-free non-parametric hazard ratio approximation that does not make any parametric assumptions on the time to event distribution. And so this ratio is formulated in terms of the survival functions and the derivative of those survival functions. And so we're able to approximate this ratio by using a non-parametric Kaplan-Meier estimator and also assuming that we have a monotonically decreasing function, so we can fix a linear function. However, more complicated spline functions can be used to reduce biases. And so here I illustrate an example of where we can use this hazard ratio to estimate the treatment effect. So we actually introduced a new semi-synthetic dataset that is based on the 8 clinical trials group. And in this dataset, we use the covariates from the ACTG dataset, and we are able to synthesize the potential outcomes using the Gombesch-Cox distribution. And we introduce selection bias here, where age and CD40 are the confounders, and we introduce sensory. And we use this so that we can sort of like evaluate our model to see whether it can recover the true hazard ratio, which here is the black line. And you can see that our model, which is CSA info, is able to sort of follow the true black line, meaning we can recover the true treatment effect, which is very close to the ground truth. And so how are we able to model the counterfactual survival analysis model? So we actually model 3 functions that are parameterized by neural networks. And so here you can see that we model for both censoring mechanism, which could either be non-informative censoring or informative censoring. And so when we have non-informative censoring here, we have 2 potential outcomes, T0 and T1, and depending on the treatment assignment, we observe only one of those. And when we have informative censoring, we have to model for both those censoring mechanisms. So here phi is an inventable deterministic mapping that maps from the covariates to the latent representation R, and we introduce 2 stochastic time to generative functions that can model the potential outcomes, and we also add stochastic censoring functions that can model for non-informative, for informative censoring. And so we're able to learn these 3 functions using an upper bound that has been previously proposed in Charlotte. And so in this formulation, we are able to account for the censoring bias based on the factual loss, which we can optimize for both non-informative censoring or informative censoring. And we're able to also account for selection bias by matching the latent distributions using the integral probability metric. And so we use the dual formulation of the Wasserstein distance via optimal transport. And so we're able to now, we have all the tools to start using observational data and to actually start to make counterfactual predictions. And so here I illustrate with the Framingham heart study, which is a longitudinal cardiovascular cohort study that we use to evaluate the effects of statins on survival time. And so here I show, for example, here we have 2 survival curves. So Y1 is the survival curve for the group that received statins, whereas Y0 is the survival curve for the group that did not receive statins. And you can see this actually observational data exhibits a common paradox because we know from clinical trials that statins is actually helpful, but here you can see that sick people actually take statins and they end up having worse off survival curves. So we need to build proper adjustments that account for these biases. And so we're able to sort of evaluate our model against competitive baselines and compare to a previously large RCT study that has shown that statins is beneficial. And so you can see here that our model, CSA Info, is able to recover the correct treatment effects of statins. Although Cox proportional overlapping weights is able to do it, we're not able to predict either the factuals or the counterfactuals. Another interesting result that we can sort of observe from using from predicting the log hazard ratio is that we can actually stratify subpopulations into a positive or negative or neutral treatment effects. And so even though statins is helpful for the population, we can sort of identify subpopulations that do not benefit from statins. And so this was quite an interesting result. And so for more details, you can refer to our paper, and in the future, we'd like to understand the sensitivity of our estimates to unobserved confounding, and also understand the effects of both censoring and selection bias on causal identifiability. Thank you.
Thank you so much for the wonderful talk. So let us now head to the final talk of the series before we go to the panel discussion. So the final talk will be presented by Sonali Parbhoo, and she'll be talking about robust machine learning methods for targeted healthcare. And Sonali is a postdoc researcher at Harvard, working with Professor Finale Doshi-Velez, and her research focuses on decision-making in uncertainty, causal inference, and building interpretable models, mainly to improve clinical healthcare and deepen our understanding of human health, with applications in areas such as HIV and critical care. Sonali's work has also been published at a number of machine learning conferences such as NeurIPS, AAAI, ICML, AI Stats, and also medical journals such as Nature Medicine, Nature Communications, AMIA, PLOS One, JAIDS. And Sonali received her PhD in July 2019 from the University of Basel, Switzerland, where she built intelligent models for understanding the interplay between host and virus in the fight against HIV. She was also a recipient of Swiss National Science Foundation Mobility Fellowship for her research at Harvard. And prior to this, Sonali received her BSc and MSc in Johannesburg, South Africa, where she specialized in molecular biology, computer science, and mathematics. And apart from her research, Sonali is also passionate about encouraging more discussion about the role of ethics in developing machine learning technologies to improve society. So with that, I'll hand over to Sonali. Please take it away.
Thank you so much. So, let's just, yeah. So thank you for the kind introduction, and I'm very excited to be here. Today I'll be talking about robust machine learning methods for targeted healthcare, and I'd like to acknowledge many contributors to this talk who have made this work possible. So machine learning has revolutionized our society in many ways, and we see this with the way we interact with our phones that can now give us recommendations of, say, what music to listen to, or our cars now have smart park assist technology. Yet despite all of these successes, machine learning has had limited success in healthcare. And this is evident from the growing number of articles that we see in high-profile journals that, warn us of the perils of AI in healthcare. Artificial intelligence makes bad medicine worse, et cetera, et cetera. And where we have seen successes, it's been limited to domains where we're natural experts, such as images. So improving healthcare actually requires evidence. And to date, as others have mentioned, the gold standard for getting this kind of evidence has been randomized control trials. Here, subjects are randomly assigned to interventions, and the efficacy of an intervention is basically measured as the difference between the outcomes of the treated and untreated groups. However, randomized control trials are expensive and they're often restricted by their eligibility criteria. So as much as we'd like to say that 90% of treatments in hospital are sort of backed by randomized control trials, in reality, only 10 to 20% of these treatments are actually based on randomized control trials. And for diseases like asthma, only 6% of asthmatics would actually be eligible to partake in these kinds of trials. And this is not because of malintent. It's not to say that we don't want to treat the rest of the individuals. It's just that when we're testing these kinds of things in practice, we want our populations to be relatively homogeneous in specific ways. And so what this amounts to is that what we get from a randomized control trial might fail to generalize across different populations. So the alternative is to fall to observational data as evidence. And this data is basically not gathered to answer your hypothesis. So you don't really know how interventions were assigned. You're just given a batch of data. And so as a result, it suffers from various kinds of confounding biases. So if you look at this example over here, at first glance, you might think that treatments are randomly assigned to these individuals. But upon closer inspection, you see that individuals that are wealthier are more likely to receive treatment B than treatment A. And so any differences in the outcomes might be a result of socioeconomic status rather than the actual treatment efficacy. And so as a result, we have to be very careful what we optimize for in healthcare to avoid sort of perpetuating these kinds of biases. And so over the course of my career, I've focused on various ways in which we can do that. And I've boiled it down to optimizing models for robustness to essentially improve healthcare. And I'll tell you what I mean by this. This means that we should understand how a model works. We should understand the data set that was used to train a model, as well as the downstream application in a clinical setting. We should have models that are not like the stack of cards. So if we remove a single card, the whole stack will fall down. We should have models that work well across populations. So if we remove some of the patients and change them with others, these models should still be able to work well. And if they don't work well, we should have rigorous enough error analysis such that we understand which groups a model doesn't work well for. And so I'm going to talk about two contributions that try to do exactly these three things. The first will be understanding a particular model's predictions and when it makes sense. And so we know that deep learning models are very powerful with hundreds of parameters that they use to make predictions that are very flexible. But the goal of this approach is basically to get robustness via mimicking or sort of emulating a clinician's simulatability or decision-making process. And so we know that we have simple models like decision trees that can actually provide intuition of why a model makes predictions. So in this case, a prediction for a patient of being high risk of a heart attack might be because the patient is tachycardic, their age is above a certain level, and their blood pressure is above a certain level. And we can understand this thought process. What these trees also enable us to do is simulate counterfactual scenarios. So what would happen if we had a different patient with sort of different conditions? And so the question we ask here is, can we optimize deep models to be interpretable in terms of small decision trees? And so we developed a procedure to do exactly that. The idea was to use the average path length of a decision tree to constrain the model's predictions. We'd start off with a deep model. It would predict some sort of decision boundary. We'd train a decision tree to mimic the predictions of the neural model, and that would give you an approximate boundary. We'd then count the average path length of the decision tree, and we'd use that as a penalty or a regularization term in the optimization to optimize over the parameters. Now, of course, this procedure is not differentiable because this is not continuous. So we had ended up using a differentiable surrogate of the tree to make this optimization tractable. What we found, importantly, is that tree regularization enables us to get this sweet spot of high accuracy predictions with trees that are relatively small and easy to understand and step through by clinicians. So we applied this to an example of predicting whether a patient should be mechanically ventilated in the ICU setting. And we showed this tree to a clinician, and they could sort of step through the reasoning and audit the predictions made by the model as a result. So in this case, you would see that you would choose to ventilate a patient if they were breathing too fast, if their oxygen saturation was particularly low, and if their comatose state or their organ function was particularly low. And this seems to make sense. coherence. Okay, so now I mentioned that, but I also mentioned that models should work well across different populations and subpopulations. And perhaps it's too much to expect a single tree to generalize across different populations. So in order to account for this, what we did was we tried to apply this tree regularization procedure over varying patient groups. The idea was instead to train multiple trees per region of the input space. And what we found is we were able to obtain a similar level of accuracy, but also found that we had different trees in each region, which could be used to distill the knowledge in each region. So for instance, for patients with good organ function, we would choose to sedate them based on their oxygen saturation levels and their comatose state. On the other hand, for patients that had high organ failure rates, basically we would choose to sedate them based on their comatose state as well as their kidney function, which seems to play a very important role in this whole procedure. And so this was very good. It helped us audit these predictions, and we could also capture sort of nuances in patient groups. However, we said that we wanted rigorous error analysis and understanding for which groups a model doesn't work well. Now, while trees can provide this sort of intuition about predictions, because we have multiple trees over different regions, we have multiple competing explanations, and they can have some sort of variance. And so we need something else. And so this brings me to the second approach that we developed, which is enforcing coherence with human expertise. So you can imagine a situation where you're given sort of a machine learning model and you have a human expert. In one of the regions, the machine learning model is very accurate, in which case you would want to rely on it. In another region, the human guideline is very accurate, in which case you'd want to use it. There might be a difficult region where you don't know what to do with the patients, which are hard to treat. And in this case, we would still like to rely on human expertise or enforce coherence with human expertise in this region. And there might be cases that are out of distribution where we haven't seen very many patients like this, and we would still want to fall back on the human notion of what it means to do something in a good way. And so our approach that we proposed was a preferential mixture of experts that enforces this actual coherence with human expertise. We fed in our human guidelines that we were given from a clinician. We got our machine learning models predictions and our patient features, and we trained a sort of interpretable gating function that allowed us to produce predictions that align as much as possible or are most coherent with human expertise. Now, this involved solving like a complicated non-convex optimization task in a game format where one of the experts or one of the players tried to essentially optimize for coverage of the human expertise or coherence with the human expertise, and the other player tried to optimize for predictive accuracy. What we found is that by doing this, we actually found the sweet spot once again of getting good coverage or good coherence with human expertise, as well as good accuracy on a task for predicting virologic failure in patients with HIV. What we also found is that, we got high accuracy predictions and we got good coverage. What we also found is that by doing this, we achieved our goal of trying to figure out where models can do well and which groups the models actually fail on. So for this task of predicting virologic failure for HIV, for instance, we found that we would rely on the machine learning very much for patients of subtype B and subtype C. These are patients in Africa and Europe for whom we have very good sequence data and we know what's going on with them. On the other hand, for patients where the virus had significantly mutated with significant numbers of recombinant forms, we would have to fall back on human expertise. And so this allows us to know exactly the failure modes of our model. So looking ahead, I've already spoken about that robustness is very important for these models, but I want to emphasize that robustness doesn't mean understanding every single thing about a model. It also doesn't mean building simple models for the sake of transparency, nor is transparency a panacea. And this is suggested by recent findings where models that were actually transparent, it turns out, could actually hamper a person's ability to detect when these models make mistakes. And this is something that we need to be very cautious about. Furthermore, models that are more transparent make people feel as if their choices are good, so they don't audit their predictions as rigorously. What we do need instead are models that basically allow us to understand when to rely on them and when to reject the output, as I've already shown, understanding whom a model may work for and on whom it fails, as well as understanding the limitations of the training data that we use when we actually build our models. So in practice, bringing this to light in terms of improving healthcare, what we need is essentially, once we have our machine learning model, we need to bring humans in the loop such that we can refine the predictions made by the models, and we get evidence that we can then use to sort of define better hypotheses for conducting better clinical trials. And if we don't have that evidence, we have to collect more evidence or stratify the data and perform ablation studies. So to summarize, what I've shown is that improving healthcare requires evidence. This evidence needs to be robust. We need to understand a model, the data set that was used to train it, as well as the downstream applications. These models should generalize across different populations and subpopulations, but most importantly, we need to understand the failure modes of our model. And while explainability and some of the tools that I've highlighted can actually help in this process, if the explanations are too simple, they can hamper our ability to sort of audit the models and result in over-reliance. And this is something we need to be very cautious about. We also need to bring humans in the loop to introduce more rigorous auditing standards in order to tackle these kinds of biases that could be propagated via machine learning models. And so with that, I'd like to thank you and conclude.
Thank you so much, Sonali, and thank you to all the 4 speakers for the 4 wonderful talks. So in the next phase, what we're going to do is this panel discussion in which we would solicit questions from the audience, and so you could engage with either of the 4 speakers and so on. So I see there are a few questions in the chat already, but I would encourage the audience to put more questions also. So to just kick off the question answering session, let me just ask one question to all the 4 panelists, and feel free to just unmute and talk in whatever order you like. So mainly, I'm just curious to know what your experiences are and what some of the main lessons are that you took from your work in AI for social good. So basically, were there any new challenges, or what are some of the key lessons that you learned from your work?
Go first.
Yeah, sure.
Sorry, there's some construction happening above me, so you might hear some knocking sounds. So there are a lot of things, but I'll try and keep it to 1 or 2 short things. I'll say one is we speak about data, the importance of data in machine learning a lot, but a lot of machine learning research is actually focused on the models, not the data. And one thing I really just came to appreciate in its full gravity is the extent of the importance of data, both how painful it is to collect data, how lengthy and painful, all of the work that has to be done to make it ready for machine learning. It's just immense, and it easily consumes, say, 70 to 80% of the time we spend on everything we do.
That's a great point, Charles. I think that anyone who touches healthcare data, even people who haven't collected it as assiduously as you have, definitely can understand the pain of unreliable data. I want to maybe add another one, which is to understand that machine learning can be 2 things. It can be unbelievably powerful in the future of medicine and amazing, and it also can be deeply flawed and dumb in ways that a 2-year-old could probably beat it at. And so I think mapping that frontier and actually understanding when the machine learning model, as mentioned in some of the talks earlier, understanding when the machine learning model will work or won't work is something that we need to know very well in order to be able to put it into an actual clinical pipeline or put it in the hands of people.
And building on that, I would say that I've come to realize how little we actually know and how much we have to rely on human expertise to actually do some of these things, and how much experience these clinicians have that can be very valuable in knowing in quantifying, knowing what we don't know, and various other things. So it's like a very closed loop cycle, I would think. I think we don't take advantage enough of like clinical expertise, and we really need to like make closer collaborations to bring things into practice, I think.
Yes, to echo that as well. I've learned that we need to approach machine learning with a comprehensive approach that accounts for the data collection or the data processing and also the metrics that we use to evaluate our models, because we need metrics that account for example, like accuracy, which is what is typically done in current machine learning, and also calibration, like model calibration is actually very important in healthcare, and also accounting for uncertainty. And in addition to that, we need to think about how these models are going to be used in practice. And I think starting to look at causal inference will be an interesting aspect, you know, in addition to just making predictions.
Excellent. Thank you, everyone. Yeah, it's really interesting to learn from all of you. And I think there are a lot of similar themes in hearing across your talks naturally. I want to go to one of our audience questions that came in. This is actually one I had as well. This was for Charles. This is from Isa Mashani from Glasgow. His question was, how do you take into consideration other features that might affect the crying sound, i.e. size of air, throats, age, etc., or size of the baby, probably, some of these different aspects besides just the cry sound, I guess.
Okay, yeah, good point. So it's worth saying one thing that helps in the case of the asphyxia problem, and then I'll come to like generally answer the question. So first, in asphyxia, it's baby is most at risk for it in the neonatal phase, so the first 30 days of life. So what this means is the demographics of the patient population we are targeting is already constrained. It's already constrained to this like newborns. I don't know if you can still hear me. I feel like it's.
Yes, yeah, we can hear you. Okay.
Okay, it's like it's disturbed me even more. So within this first 30 days of life, you know, we have this small demographic that we focus on, and so there's not a big age variation between 0 and 30 days of life. But following that, some of the new work we're doing now is expanding to other clinical conditions, because really the idea of cry diagnosis is a central nervous system thing. And so there are other conditions that affect the central nervous system, which we can also detect from the cry. And so we are looking at both acquired CNS conditions and congenital conditions like encephalitis, hydrocephalus, and Down syndrome and other things. And so when we look into those ones, it's possible we might need to factor in the age of the patient we are considering and other like variables. When the case of asphyxia, it's really just the cry we're using, and our data so far shows that it's pretty, it's working pretty well.
Interesting. Thank you, Charles. So let me take one more question from the audience. I'm not entirely sure who this is for, but I'm guessing it's for Paidmoyo, but if not, please correct me. So the question is, could you please explain more what censorship bias is, and potentially with a simple example?
Yeah, I think also Irene can also chip in because her talk also talks about like left censoring. So my work actually focuses on right censoring. So basically we have different censoring mechanisms when we collect data, and I think Irene will talk about left censoring, and we also have interval censoring. So in terms of right censoring is that when we do clinical trials, we have patients who drop out of the study. So we do have, like, for example, when we're interested in predicting their survival time, whether they lived or died, we only know that they were alive by the time they dropped out of that study. So that's a scenario of right censoring. And I give to Irene to explain left censoring.
Yeah, left censoring is actually something that's not super well studied. I think that most of the censoring analysis does focus on right censoring. I think the left censoring comes up in the context of we don't have reliable measurements of people before sometimes. So in my talk, I use the example of diagnosis, but we could imagine people don't get health insurance, and then once they do, they enter the healthcare system, or they, for whatever reason, are not being collected. One way of mitigating this, in addition to what I mentioned about inferring this through a latent variable, would be collecting a lot more data about more comprehensive data sets about people. So I've seen other analysis where you go to maybe countries where they have national healthcare and they have data sets that you can use, or you use a more comprehensive set like an insurance claims data set, although that obviously has its own flaws or its own challenges as well. So I would say that both left and right censoring are probably important things to keep in mind, thinking about where your data comes from and why it might not be its complete form in front of you.
Excellent. So I think we have some more questions coming in. We've invited people also to raise their hands. And if you have questions that you'd like to ask yourself, I see first on my list here is from Grant Fleming. So if you'd like to unmute and ask your question, please go ahead.
Sure, thanks. And thank you everyone for the talks you've given so far. It's been very helpful for me to help contextualize these issues better. The question I have, I think could be answered really by anyone on the panel. So I guess anyone feel free to jump in, but I work in industry, and fundamentally, we want to not just identify these problems, but have some sort of plan in place to help the client mitigate them. And I'm curious, from your perspectives, how much time and effort is worth spending on technical mitigations for biases perpetuated by a model, whether that's gathering more data, changing the way the model is specified, or changing some sort of mitigation method you use, versus advocating for some sort of procedural change. So changing the operating procedures within the hospital, or basically anything not related to anything you would do in the code.
That's a really interesting question, Grant. I would say, certainly both are definitely going to be useful. There are tools, for example, uncertainty estimates for when we do bias audits that can give you insight into, is this a matter of, oh, we were 0.51 as opposed to 0.50, or is this sort of an egregious error? I think, going back to a point that was mentioned earlier, it would certainly depend on the domain experts in thinking about, oh, what would a risk score, or what would some sort of model output be even useful for, or could we sort of temper the expectations about, oh, we just always go with what the score says, versus actually we do know for some kinds of patients the score is not super useful or super accurate, and therefore we will lean more on an expert, going actually to other themes by speakers today as well. So I think that's sort of, yeah.
Wonderful. Thanks for adding that. So I see one raised hand, but there is also one question in the chat. So before it gets lost behind a lot of messages. So I think this is asked by Ahmed. So Ahmed, do you want to unmute yourself and just ask, or I can read it out? So, okay, maybe let me just read out the question first. So he says, I saw something related to predicting a patient that will die in the ICU. Is it possible to also work on predicting a patient that will not come out fine after cesarean section?
I think that was probably addressed to me. Yes, that's totally something that would be possible to predict. Outcomes after cesarean sections would be a very definite label, and then you would want to collect all patients as people who are going into cesarean. The key question actually though would be, what would you use after you get that score? There are many different reasons why a patient might have a poor outcome after cesarean. So there may be some sort of stratification in terms of what an intervention would look like. But as far as a very classic machine learning problem, yes, you could definitely predict outcomes from the cesarean section.
Just to piggyback on that, Irene, I'm wondering if there are any specific kinds of censorship that you would have to think about in that scenario? Any that would be different from other
It's
settings?
not
Sorry to
quite
put you on the spot.
censorship, but there's confounding in treatment. So there is evidence that patient clinician concordance has an impact on outcomes. So for example, if you and your doctor are the same race, you'll have better outcomes than if you are slightly different, if you are different races. And so that kind of confounding can have an impact on the data that is being collected. And maybe you don't need to, you didn't think to check for this particular tweak, and therefore, you draw different outcomes. I would say in the context of predicting, so if you assume the world is going to be the same as it was in the context that you collected the data, then that is a fairly straightforward machine learning algorithm, even though there may be subtleties behind the wheel. Of course, caveat for everything that goes on in healthcare for the next few years, if this data is collected in, say, 2020, then maybe you don't, there's a lot of other, not even censorship issues. I guess censorship in that people didn't, people were scared to go to the hospital, but there's sort of other factors to keep in mind as well.
Great, thank you. So I see Chooks also has a hand raised. I'm having some trouble hearing you.
Yeah.
I think so, yeah. Please go ahead.
All right, so I would like to say great talk and good job to everyone. I have 2 quick questions for Sonali. The first one is at the beginning of the talk, you said you made mention of something about eligibility criteria.
Still can't hear you clearly, I think.
Sorry, can you hear me now?
We can't hear you. Maybe you could type your question in the chat window, please.
Okay, all right.
Yeah, I'll be happy to read it out after you type it in. I think that would be great. Thank you, Chooks. Aditya, do you have a next question here from the chat?
In the meanwhile, maybe we can go to Isa, who has also raised their hand.
Yes, thank you very much for the nice presentation. I just have a general question to our rising stars. Anyone can jump in and answer. I'm curious to know what will happen in the future concerning artificial intelligence. We know now we are just developing these machine learning models, the IA models, to do some diagnosis and number of things in health research. Do we think maybe at the future this model could work independently, or we still want someone with a professional expertise to work behind these models in order to make sure that we are doing a perfect thing in the hospital? What's your thought concerning that? This model could we reach a point that we just only have algorithms work there without any professional who is trying to validate what the model predicts?
I could say something here. I mean, my response to this, I won't be the first to say this, but I think that we will always need humans in healthcare delivery. And I expect AI to help us remove mundane tasks from the hands of the health professionals and potentially do 2 things. One, release experts to spend more time on the more difficult things and things that require human abilities. And secondly, it would also extend the skills to do complex diagnostics to people who do not necessarily have, who are not necessarily specialists, maybe just they are midwives and not neonatologists, for instance, but yet they can do screening for particular conditions with just a simple tool. So I think those are like 2 areas we'll see AI help, but not replace the physicians altogether.
I'd like to second your opinion on that. I think that where we will see AI helping humans is where humans already to some degree are natural experts in certain annotations and things. They might make those mundane tasks, as you've already said, easier to do. In the long run, I see more of like a human-computer interaction sort of system where the computers actually help us develop new insights, and then we use that to sort of hone our expertise and then refine our sort of judgments about how to act in practice, in clinical practice, but I don't see them replacing humans in any form. And subsequently, you could also inject that expertise back into the model and have this synchronized sort of human in the loop process.
I also want to plug telehealth. I think that that's something has been floated around a lot, is that right now people have to see a practitioner and the resources there can be limited. And so maybe there might be a world where, you know, I have a certain amount of symptoms. Am I really, should I really go to a hospital and see someone and potentially have to pay some money just to see a clinician? So maybe if there were an additional layer where either an AI could help triage, oh, it's totally fine, or say like, oh, maybe there's something going on, maybe you should go to, or you should go in. I think that could also be an extra amount of help from the patient side. Although I should say this is something that would need to be done very carefully, very carefully.
Thank you.
Yeah, I also wanted to add that I see AI being used to inform health policy, because right now, actually, like we are already using AI in the, machine learning approaches in like risk predictions, and it's being used, for example, for many of the chronic illnesses that we have, like for example, for type 2 diabetes, when you go to the hospital, there is some protocol that doctors use to decide whether they should screen you for something, and that is just based on like some risk prediction scores that have been formulated before. And so where I see AI is sort of, maybe we should revisit those risk prediction scores that have been made in the past, and try to see whether, with all the data that we have collected, whether those scores are still relevant or not.
Yeah, thank you for all those excellent points. I want to go to another question in the chat that I think piggybacks off this a little bit. I'll direct this to Sonali because I think it's most related to your talk. How can we create a corpus of knowledge to replace the human experience needed? It would be something like connecting the models to a pre-built DB. And I think, so we've had some good comments from you about, you know, humans, we still need them in the loop, but what I'm wondering, I'll add sort of my own thought on this question too, is if there's a way, you know, when you're doing this iterative process, you're getting some of the human expertise, right? Is there a way to sort of distill some of that expertise you're getting to have available in the future for other models, things like this?
So absolutely, I think there are many ways in which you could do this. I will emphasize that I don't see it as like a once-off process, as I've already said. It's not something that happens after you build a model. Maybe there's even ways of like getting human expertise in what features are meaningful for building the model in the first place. Maybe it's actually optimizing the model to be interpretable, as I showed in one of the examples. And then maybe afterwards, it's like this post hoc sort of human expertise that you might include. So it happens throughout the process. Yeah, I'm not sure if that answers the question, but I think you would need human experience at each stage of the pipeline is what I'm trying to say. So I don't think you could essentially replace it entirely, but you could start, if you wanted to see where, say, human expertise is most helpful, you could start by plugging the experience there and seeing like what it does to your predictive accuracy, what it does for your downstream applicability or usability of the model in practice, and then take it from there and see which other parts of the pipeline sort of need human expertise and need more anchoring.
Excellent, thank you. I think
So I have one question which was sent to me as a direct message, so let me read it out. I think this is a question from Stuart. So the question is for the entire panel, and it asks whether there is any chance to build a general diagnostic model that could work with different databases for different illnesses or diseases, or a family of diseases, because building models for each individual disease or malady seems very inefficient? Or will such a general model be very high level that it will be just useless?
I can sort of take a so I think in terms of building general models, I think we may want to sort of look at more molecular data, like my recent work that I've been working on, which is immunomics, in terms of like diagnostics, because just using covariates that are pre-selected for a particular disease would be sort of difficult, to sort of start to do diagnostics at a large scale. Hopefully with like some of the recent advances that we've had in biology, we can start to incorporate molecular data, and that can sort of give us a more comprehensive way to sort of evaluate a particular patient.
So I think we can go to another question here from Arsal. And this is, I think, a pretty high level question, but which certain sections in healthcare do you think need extensive AI research at the moment, like an AI approach can benefit greatly? I like this question, especially given the broad expertise we have from this panel.
I would say that all of healthcare right now is up for grabs. Anything where there's a fair amount of data, I think is a promising place to start. There was a great comment in the chat about working with domain experts in a continuous process. So obviously there's a need to ask maybe clinicians, like what is the biggest pain point? Where do you think an automated, sometimes dumb, sometimes brilliant machine could be helpful here? And what do you think would be useful? I think if you asked a lot of clinicians, I'll give you an earlier point, a lot of the grunt work that they do is super boring and not something that they want to do. And that's what they would want the most help for. And so there's a need to think about what would be, one, viable with machine learning, so lots of data, clear labels, et cetera, and then two, useful to the system in terms of if we could actually spend years and years hammering this away and really solve this, would it be helpful to people at large, and going from there.
Okay, so we are almost nearing the end. So I also want to give all the speakers a minute or so to wrap up, but let me also just quickly take the question from Jux because he has typed it out in the chat. So there are, I think, 2 quick questions for Sonali. So first is that at the beginning of your talk, you made mention of eligibility criteria. Could you please shed more light on what that entails? And the second question is that when you talked about robustness of a model, you talked about not making it too simple and about transparency not being a panacea, but could you please explain how simple is too simple? And by this, I mean, is there any limit to the simplicity?
So for the first part of the question, this is generally how randomized control trials are conducted. At the moment, we're seeing this with like AstraZeneca, where they're testing their vaccines now on children before they test. So previously they had tested them on adult populations to see like how would it respond in COVID. And now they're testing it on children populations. So they can't test on adults and children at the same time because these groups are maybe too heterogeneous and they won't be able to get accurate results in terms of like understanding whether the particular vaccine is efficacious or not in a particular setting. And so they often have these criteria that in order to participate in this sort of clinical trial, you need to meet X, Y, Z. And clinicians and domain experts who are building these kinds of tools, they sort of make this very clear. And then they'll give patients like a placebo, or they'll give them the actual vaccine, and then they'll measure the difference between those. And then to the second question, when I talk about the robustness of a model and not making it too simple, there was that paper that I referenced in the presentation itself. And basically in that paper, they found that they were trying to predict, I think, housing prices or something in New York. And they found that, like, obviously a model that could predict the housing price of, say, a house with 5 bedrooms would be very different to, say, if you were to have a house with 1 bedroom and, let's say, 6 bathrooms. That could still be in the similar sort of range in terms of the number of rooms as the former house, but because it only has 1 bedroom and 6 other bathrooms, the price could not be comparable. And so if you find that your features that it's using are, for instance, the number of rooms in total to make these kinds of predictions, these predictions then become sort of nonsensical. And so you really need to take it in the context of a particular application and be very careful about, like, when you audit and see what features it's using, that these seem to make sense and that they're not too simple, or they're not overly simplifying. So in the house example, it would just be using the number of rooms, which is obviously wrong. And so there is a limit, but that is very much dependent on the application, I would say.
Excellent. Thank you so much. So I want to quickly give each panelist about 30 seconds to wrap up and say any closing words, and then we'll thank the speakers. So we'll just go in order of the speakers. I believe Charles said he can't speak. If you can, please tune in now. Otherwise, Irene, go ahead. Charles, if you would type it out, that'd be great.
All right, Charles gets, so just any closing words, just anything on my mind?
Right, any final thoughts, any advice for aspiring AI for social good researchers?
I would say the field changes in ways that you cannot even imagine. When I started my PhD, no one was working on fairness, not really. And certainly no one was working on bias for health. And certainly no one was, things like CRCS didn't exist yet, that would bring together people from, all kinds of interests working towards a common goal. So I would say, it's a little generic, but work on the things you really enjoy. If you think you're the only one working on it, you're not, and the field can change very quickly, quicker than you think. So I would say make sure you enjoy your research. Maybe reach out to people. Maybe that's my reason. Yeah. Sorry, this is a little incoherent. Hopefully the next one will be better.
Yeah, I would say, I guess healthcare is an interesting and exciting place to be, to work on, mostly because of the impact that your work can have on people's life, but also because the problems are quite interesting and challenging. And like the recent advances that we've had with in the biological sciences are quite exciting, and there's like more potential to explore and grow. So yeah. Thank you.
And I would say that I would think that this is a very exciting time and place to be working in healthcare at the moment. I would also like to say that I encourage people to reach out to different kinds of people that they're not usually in touch with. So just because you're working on healthcare doesn't mean you only need to talk to clinicians. You should also be talking to ethicists. You should also be talking to policymakers and have very sort of interesting discussions about what it means, let's say, to be healthy, and what does a model's implications have in the long run. And these kinds of discussions can really, like, asking those kinds of, maybe those interesting questions, like what does it mean to be healthy, can really help direct the field, I think, in the right way. So I would encourage people to do that. And then I'd also like to say that I really like CRCS's initiative, and I think they should continue doing what they're doing to inspire lots of other people to get involved. So thank you for having me.
Perfect final note to end on there. Thank you so much, everyone. Thank you for your great talks. This was very exciting. Lots of interesting learnings from all of your expertise. So let's give one final round of applause to all of our speakers. Thank you so much. I guess we are about a minute over time, so we'll end there. And if you have any questions, please feel free to email us. And yeah, take care.